back row tutoring. In this video we're going to be looking at power and wasted energy, and this is the second part of the first topic of energy. So let's get right into it. Okay, so in fairness this next part is quite boring, and I do apologise for that, but it is part of the GCSE, so we've just got to crack through it, and that part is specific heat capacity. So the specific heat capacity of a substance is the amount of energy required to raise the temperature of 1 kilogram of the substance by 1 degree Celsius. Yet another formula is given for this. However, you do not actually need to learn this formula as it is given to you on the day of the exam. You only need to know how to use it. If you know the change in thermal energy, the mass, and the temperature change, you can work out the specific heat capacity of a material. And that's because delta E is equal to mc delta theta. The change in thermal energy is equal to the mass multiplied by the specific heat capacity multiplied by the change in temperature. So the change in thermal energy, that's in energy, so that's given in joules. The mass is kilograms. The specific heat capacity is joules per kilogram degrees Celsius. And the change in temperature is degrees Celsius. So we're going to do a little work example now. So lead is a metal used in making salt. Salt must be processed in a heated environment with a minimum temperature. Lead has a specific heat capacity of 1600 joules per kilogram degree Celsius and requires 300 joules to heat up the temperature. If the mass of metal used was 40 kilograms, by how many degrees did the block heat up? So that's quite a wordy question, so we'll decompose that. What we want here is the delta theta, the change in temperature. And in this occasion, we have the change in temperature on the right-hand side. We'll have it here, and that's what we want to work out. So 300, the change in energy, is equal to 40, because that's the mass in kilograms, multiplied by 1600. That's the specific heat capacity of the lead. We're going to rearrange this formula slightly. We're going to bring the 40 and the 1600 multiplied together onto the left-hand side. So we're going to divide both sides of the equation by 40 times 1600. So we've done that here. Evaluating 40 times 1600, we get 64,000. So our change in temperature is equal to 300 divided by 64,000. Evaluating that, we'll get 0.0047. Change in temperature is in degrees Celsius, so our final answer is 0.0047 degrees Celsius. Okay, so we're going to watch a little video now of how to find the specific heat capacity of a material, and this is a required practical, so if I were you, I would try and learn this quite off by heart. Hello there. We're going to be calculating the specific heat capacity of a material, and this is one of the required practicals. So for this required practical, you will need a beaker, a balance, a material to measure the specific heat capacity of, and in this example we'll be using cooking oil, an immersion heater, thermometer, bubble wrap / thermal wrap, joule meter, power pack, and a lid for the beaker. Okay, so we're going to start by placing the beaker onto the balance. Press the 0 button now, so any mass which you add on top of the mass of the beaker will be counted only. Fill the beaker with oil and record the mass of the oil. Next, place a thermometer and an immersion heater into the oil. You need to record the initial temperature of the oil as shown on the thermometer before we add any heat to the oil. Now we'll place our insulating material around the outside of the beaker and place an insulating lid on the top. Connect your immersion heater to a joule meter, a device which records the electrical energy transferred, and a power pack. You now need to wait for 20 minutes, and once this time is up, you need to record the measurement on the joule meter. Also record the new temperature of the oil using the thermometer. Here is the equation for energy transferred with relation to specific heat capacity. Energy transferred is mass times the specific heat capacity times the change in temperature. Now we want to find our specific heat capacity, so we need to rearrange this formula. Once we've rearranged it, we get that the specific heat capacity is the energy transferred divided by the mass multiplied by the change in temperature. And here's some values from the experiment. Initially, the temperature was 20 degrees. In the end, the temperature was 43.23 degrees, and the mass of the cooking oil was 0.54 kilograms. 20,706 joules of energy entered the system. So we're going to plug all those numbers into our formula. We have the 20,706 divided by 0.54 multiplied by the difference of 43.23 and 20. Evaluating our equation, we get that our specific heat capacity for the cooking oil is 1,651 joules per kilogram degrees Celsius. Now, in the exam, you could be asked about potential sources of inaccuracy. One source of inaccuracy is thermal energy or heat escaping the beaker through the gaps in the lid or through travelling through the insulation. Another source of inaccuracy is that the energy being converted from electrical energy isn't all passing into the oil's thermal energy store, especially if the immersion heater is sticking out of the liquid. And finally, the thermal energy may not be spread into all parts of the cooking oil. To help this, you should stir the oil. So that is a required practical, so I would learn that if you can, and those final bits there about the sources of inaccuracy. Examiners do like to test the students on the knowledge of inaccuracies, and I would learn all of that, but that last bit there is quite important because that could come up in an exam question, I can imagine. So if an object is harder to heat up and takes more energy for the same mass, does it have a high or low specific heat capacity? Well, it has a higher specific heat capacity. If you have something which is harder to heat up than something else of the same mass, then it has a higher specific heat capacity. It's harder to heat up. If you're following along in your revision workbook, now complete task 5 and pause the video. We're now going to move on to power. Power is defined as the rate at which energy is transferred or the rate at which work is done. Power is measured in watts, and 1 watt is equal to 1 joule of energy being transferred in 1 second. This leads us onto our next equation for power. Power is equal to work done divided by time. Power is measured in watts, work done is measured in joules, and time is measured in seconds. Right, we're going to have a look at a worked example now. Motor A of power rating 300 watts lifts a weight of 900 kilograms. An alternative motor, motor B, of 500 watts lifts a weight of 900 kilograms, the same weight. Which motor lifts the weight quicker? Well, power is the rate of energy transfer. This means something with more watts or more power will transfer more energy in the same amount of time. Therefore, the motor with the higher power rating will lift the exact same load quicker, motor B. So just revisiting that, motor A and motor B, they both are lifting the same mass. They are both lifting 900 kilograms, so they have the same force to contend with. But because motor B has 500 watts of power, it can handle more energy in the same amount of time. So you can go through more energy in the same amount of time. So if you gave both motors, say 30 seconds, within that 30 seconds, motor B might have lifted that load, but motor A might still be lifting it after those 30 seconds have passed. Another worked example, a light bulb with power rating 100 watts is turned on for 5 minutes. How much energy is transferred? Well, write out our equation. Power is equal to work done divided by time. Our unknown here is the work done. We'll have 100 is equal to W over 5 times 60. Remember, the unit for time is always seconds. So if you're given minutes in the exam, you have to convert to units. So 5 multiplied by 60 is 300. So again, our unknown here is the W, our work done. So by rearranging this formula, we're going to multiply 100 and 300 together to get our work done. So we'll get an answer of the work done is 30,000. The energy transfer or work done is measured in joules, so the final answer is 30,000 joules. And a slightly harder worked example now. A 3 kilowatt motor pulls a 500 kilogram slab of concrete a distance at 2 meters per second. How long did it take for this motion to be complete? Well, this question requires the use of two formulas, okay? The formula that we've just learned, power is work done divided by time, and a formula from earlier on in the course from the last video. That formula is work done is equal to half the mass multiplied by the velocity squared. So we want the time. The time is the unknown here. But in order to work out the time, we need to work out the work done, because the power equation involves work done and time. We are given power, but we aren't given the work done. So we need to work out the work done in order to plug it into the power equation. So our work done is equal to half the mass times the velocity squared. Well, half of 500 is 250 and 2 squared is 4. So 250 multiplied by 4, that gives you 1000 joules. So the work done by that motor is 1000 joules, or 1 kilojoule. Now, we know that the motor has a power rating of 3 kilowatts. So 3000 is equal to 1000 divided by time. Rearrange this formula to get t by itself. 1000 divided by 3000 is time. So our time is a third. Because the time is measured in seconds, my final answer is a third seconds, or a better way to write that would actually be 0.33 seconds. So the final answer is 0.33 seconds. If you are following along in your energy workbook, pause the video now and do task number 6. Okay, so next we're looking at conservation and dissipation, the conservation and dissipation of energy. Energy can be transferred usefully, stored, or dissipated, but it can't be created or destroyed. Again, we covered this in the first video. You cannot create nor destroy energy, you can only transfer it. But that doesn't mean the energy transfer is all good. A closed system is an environment where work is done, but there is no loss of the overall amount of energy. Can you think of any closed systems? If a runner of 300 joules of energy skids along the floor to a stop, all of that energy will be transferred into sound and heat energy. Energy transfers can be useful, or again, they might not be useful. In all energy transfers, some energy is dissipated and stored in less useful ways. For example, in speaker systems, electrical energy turns into sound energy, which is a useful transfer of energy. However, some of the electrical energy which flows into the speaker is turned into heat energy due to friction and moving parts, and that's not useful. So that's quite obvious. When you turn on a speaker, you want to have sound energy. That's why you have a speaker. You want to hear the sound from whatever you're listening to. But because there's moving parts within that speaker, you have friction, and the friction produces heat. So some of that electrical energy is being converted into heat energy, and that's less useful. You would say that this energy is being dissipated, it is being changed into a less useful store heat. Can you come up with any more examples of wasted energy in closed systems? Well, I'll leave that up to you. Have a little think, see if you can come up with any. For now though, we're going to have a look at Sankey diagrams. Sankey diagrams are useful for visualizing how much energy is wasted. An arrow pointing downwards illustrates energy being wasted. An arrow pointing to the side illustrates energy being transferred into useful types of energy. This is a picture of a Sankey diagram. So this example is for a filament bulb. So you can see from the left you have 100 joules of input energy. Only 10 joules of that, because it's pointing to the right, is transferred into useful energy, and that's light, because you know when you have a bulb you want that to produce light. 90 joules out of that 100 is wasted, and that's turned into heat energy. So an old filament bulb, that produces a lot of wasted energy, that produces a lot of heat. We're now going to have a little look at this video which shows you how to draw Sankey diagrams. Hello there, we're going to be drawing Sankey diagrams. In order to draw Sankey diagrams, you must know the total input energy, the useful output energy, and the wasted energy. You need to come up with a scale. Your scale will depend on how large your energy values are. Your total input energy comes from the left side. The thickness corresponds to the amount of input energy. Useful output energy goes to the right, and wasted energy down below. A kettle takes in 500 joules of electrical energy. Of those 500, 375 joules go towards heating the water, and 125 joules gets converted into sound energy. Draw a Sankey diagram to show this information. So 500 joules of input energy, our scale will be 100 joules per square. 500 divided by 100 is 5, so our input energy is 5 squares in width. 375 joules divided by the 100 scale is 3.75, so our useful energy is 3.75 squares in thickness. Finally, we have our 125 joules of wasted energy that would draw on the bottom. 125 divided by 100 is 1.25, so our thickness is going to be 1.25 squares. Sometimes, at the end, we add in labels. So that shows you how to draw Sankey diagrams, and again, could come up in the exam, so it's worth knowing roughly how you draw Sankey diagrams. Again, if you're following along in your revision workbook in the energy workbook, complete task 7 now. Thank you very much for watching. Workbooks and test papers which integrate with these videos and online courses are available at our website, backrowtutoring.com.